Hi, I am Ganesan and now we are going to discuss about a small topic in nacelle structure. Before I enter into the topic of nacelle structure, we are in a need to know what is a nacelle and what are its types and what is the function of a nacelle in an aeroplane or aircraft. Here, first, nacelle is a housing or a structure which covers the entire part of an engine as well as the exhaust. Here, starting from its inlet rod to the exhaust, everything is being covered by a nacelle. In order to get a better performance of an engine, a nacelle has to be designed in a proper way so that it has to satisfy what are the requirements of the aircraft. What are the requirements which is aircraft which has to be certified by which has to be certified for latter processes. Here, first, in order to know what is a nacelle, it is a entire structure which is attached to the pylon, which the pylon is attached to the wing of the aircraft. Here, the entire nozzle consists of the engine as well as the exhaust of the engine has been assembled inside the nacelle. In order to get a better performance, here a high bypass ratio is to be controlled in the nacelle structure. Bypass ratio in the sense the air which is flowing, which is being sucked inside to the engine has to be only 30 or 40% of the air which is coming from the atmosphere has been subjected into the engine, and the combustion process take place with respect to the air which is sucked into the engine, and this has been subjected to exhaust. Only the exhaust with respect to the thrust which propels the aircraft in the forward direction. Here, the rest of the 60% of the air which is being sucked inside has been propelled outside with respect to some of the which helps us in thrust reversing process as well. So, in order to increase the efficiency of a nacelle, we are just designing a nacelle with respect to specific design criteria with a higher bypass ratio values. Here now we are going to discuss about what are the functions of the nacelle. For a high
difference between nozzle and this nacelle.
Nozzle is a structure which covers the entire portion of the engine, starting from its inlet through the inlet throat to outside exhaust. Whereas nozzle is engine exhaust area where where it improves the exhaust with a higher velocity in order to propel the aircraft in a forward direction. This is the difference between nacelle and nozzle. Here now we are going to discuss about what are the functions of the nacelle. Here, nacelle helps as an intake which sucks the air from the atmosphere, and it is subjected to the engine fans so that it helps us in picking up the air, which helps us in subjecting the air which has to be sent to the combustion chamber for a better thrust value. So it helps us an intake process, whereas another function as well as the better advantage of using this nacelle structure as well as the function of nacelle structure is helpful in thrust reversing processes. Then what is meant by thrust reversing processes? In most of the cases, when compared to the weight of the engine as well as due to its structure, at the time of landing, the large force has to be get into the ground with respect to its atmospheric pressure as well as its velocity. So, in order to for a proper safe landing, we are in need to reduce the velocity of the aircraft. So, we are going for a thrust reverse process. Here, thrust reverse reduces the speed of the thrust which is being exhausted by a nozzle, so that it prevents it helps us in forcing in a backward thrust, so that it helps us 40 to 50% of backward thrust helps us in controlling the aircraft due to its safe landing. So nearly 20% of the landing is carried out using the thrust reverse processes. The thrust reverse helps us in most of the conditions like that. If it is in a that is in the winter season, if the run path is not in a good condition, in the sense it may be ice, it may be covered by ice, so that here the thrust reverse processes are used in order to control the aircraft with respect to the velocity, in order to reduce the runway of the aircraft. Here it is also used in the noise suppressor processes, whereas the exhaust gas or the inlet gas which is sucked from the engine develops a noise with a higher velocity, with a higher noise, so that it helps us in controlling the noise which will be acceptable kind of noise, so that it should not affect the atmosphere, which should be acceptable value, so that it helps us as a noise suppressor as well. What are the types of nozzle which we are going to discuss about, and what are the types which is available in the sense the types of nozzle has been a separate exhaust nozzle as well as the mixed exhaust nozzle. What is a separate exhaust nozzle as well as a mixed exhaust nozzle? Here the separate exhaust nozzle is nothing but it covers the area of the fan duct as well as the core duct of the engine, so that here this is the separate exhaust nozzle, and this is the diagrammatic representation of a mixed exhaust nozzle, whereas here the processes which is the flow of the air is being separated, so that some of the process will be carried out at this area, and the flow from the flow of the air from the fan is been subjected to the engine area at this area, so that there is a separation of flow which results in a better performance of the aircraft. Whereas in the mixed exhaust nozzle, here it works here both of them are being covered in a single area, in the sense, whereas with respect to the separate exhaust nozzle, in the sense the nozzle is at the end of the nozzle area. Here it is actually using for a better performance we are going for a mixed exhaust nozzle, as well as for a low friction drag we are using a separate exhaust nozzle, which helps us in a local aircraft which we are using for day to day for us, whereas the mixed exhaust nozzle are mostly used in high performance engine, as well as which requires for trading purposes as well. Then what are the components of the nozzle which is present for in an aircraft? Here what are the components which you are going to see is the engine cowling, the inlet cowling and the fan cowling, thrust reverse as well as then core cowling and the exhaust nozzle and exhaust cone. Here what is meant by engine cowling? Engine cowling is a surface which covers the engine part, starting from its inlet to the combustion chamber of the engine. Here engine cowling has to be designed in order to maintain its aerodynamic structure before it has been designed or it has been subjected to the structural analysis. Here inlet cowling, what is the inlet? What we are going to discuss about the inlet cowling, in the sense it is the first part of the nozzle, whereas inlet cowling starts from the throat value of the throat starts from the throat of the nozzle to the fan of the engine. Here it is a counter opening as well, which helps us in extracting the nozzle, extracting the air from the atmosphere, and it is subjected to the fan to the engine, which helps us in combustion processes. Here the fan cowling is a sleeve. It is a circular sleeve, so that which is used at the combustion, which is used at the core of the engine, so that whenever some renovation work or if there any repair has to be carried out in an engine, we can just a hinge of this sleeve have been maintained, 2 to 3 hinges have been maintained, so that we can remove those sleeves and we can go for a repair work in the fan cowling. Here fan cowling helps us as well as the fan cowling consist of 2 or 3 doors, so that minor problems can also be checked during the inspection process. Then, with respect to the thrust reverse helps us in controlling the aircraft at the worst condition of the atmosphere, so that here thrust reverse can be divided into 2 types, in the sense the clamshell reverser as well as in the gasket thrust reverser. What is the difference between these two of the thrust reverser? Here, when the exhaust gas enters into the inlet of the nacelle, here the exit of the nacelle consists of the scoop-shaped door, which helps us in controlling the exhaust gas from the engine, which has been diagrammatically shown here. Here, when the thrust reverse is done, when the thrust reverse process is carried out, here these doors have been sliding at this area, whereas it helps us in controlling the velocity as well as the speed of the exhaust gas. So in the clamshell reverser, the inlet gas, that is in the sense the gas which is entered into the throat, as well as the gas which passes through the engine and the combustion process take place, and the thrust which is ejected from the nozzle also being controlled, and it is being subjected to a backward pressure, so that it helps us in a thrust reverse processor in clamshell reservoir. Whereas in gasket thrust reservoir, here only the inlet gas, that in the sense the inlet air which comes into the nacelle alone has been eliminated, that in the sense it has alone been translated to the atmosphere in order to satisfy the thrust reverse. Here the graphical representation of the gasket thrust reverse is being shown here. When the exhaust, when the atmospheric air enters into this area, where in the sense the nacelle area, only 30 to 40% of the gas or the air which enters into the engine and the combustion process is carried out over this area, and the exhaust as the thrust is eliminated at the end of the nacelle, whereas the rest of the air which is being eliminated through this area. So in order to obtain a thrust reverse processor, this valve which helps us in reversing the gas which is subjected into the engine. Here it shows the graphical representation of it. Here the air enters into here. Then in order to provide a thrust reverse, this nozzle this valve has been closed with respect to the engine, so that the air which enters helps us in it helps us as a backward pressure in order to stop the aircraft with respect to the run rate. Now we are going to discuss about what are the design characteristics, what are the design parameters which are in need to consider in order to design a nacelle, so that we can get a better efficiency with respect to the bypass ratio. Here, first we are going to design about the nacelle. We are going to discuss about the nacelle design methods which we are going to follow here. The first one is before going for a construction of a nacelle or a designing of a nacelle, we need to justify about its efficiency, as well as based on the performance of the engine only, the nacelle design has been carried out, so that with respect to the engine performance, the input throttle is to be maximized, or based on the engine performance only, the diameter of the input throttle is calculated, so that based on the based on the value of the exhaust, based on the value of the efficiency of the engine only, the nacelle has to be designed, as well as it has to be subjected to the aerodynamics. It has to satisfy the aerodynamic performance as well. Aerodynamic performance is the structure is being subjected to stress analysis when it is in motion, in the sense it is subjected to a high pressure and atmospheric temperature and pressure, so that it has to withstand its structural without any deformation. So these are comes under aerodynamic structure, so that nacelle should be designed in the form that it should satisfy the performance of aerodynamic as well. First, we are going to deal about the four-body design method. Here, the nacelle design method has been divided into three parts, in the sense First one is the four body design method, and the next one is the middle body design method, and the third one is the after body design method. What is the first body design method? First body design method is the portion which starts from its lip structure, that is in the open throat, to the middle area, that is the maximum diameter of the nacelle. In the sense, the middle area, middle body design method helps us is in the sense cylindrical shape, the diameter of the nacelle. So we are not going to concentrate over on the middle body design method. Whereas the after body design method is starts from the outer diameter of the middle body structure to its thrust, and that is the exhaust of the nozzle. Here, the design procedure has to be carried out with respect to these three types, in the sense four body design as well as the middle body design and after body design. Here, with respect to the bypass ratio, we are just going to calculate what is the throttle diameter. Based on the performance of the engine only, we are going to calculate what is the throttle diameter which is required for the supply of air, that is in the sense which is need to extract the air from the atmosphere to the engine. Based on the Mach number, we can calculate what is the throttle diameter of the nacelle, so that with respect to the throttle diameter, we can calculate what is the highlighting diameter. Whereas the throttle diameter is mentioned, this area is a throttle diameter area, whereas this area, graphical representation of a nacelle has been calculated, nacelle has been shown, so that the dimensions and the dimensions of a nacelle has been calculated with respect to the four body diagram. So here it shows the throat diameter is calculated with respect to the engine performance, so that here throat diameter is the area which covers between this area, whereas the highlighted diameter of this area is from this area to this area. With respect to throat diameter, only we can calculate the highlight diameter as well. Then we can find out what is the contraction ratio between the throat, what is the contraction ratio of the lip, that is in the throat value. Here the contraction ratio is the ratio of the highlighted area square of the highlighted diameter with respect to the throat diameter. It normally ranges from 1.2 to 1.35. Whereas for then we are going to discuss about the four body length. In the sense, this is the area where we are need to calculate the length in order to maintain a better drag flow, in the sense without any spillage drag. So we are need to concentrate more on the length of the nacelle. Here, four body length is calculated with the help of calculated using the formula, the highlighted diameter with respect to the maximum diameter, with respect to maximum width. If the length of the nacelle is increased, then it causes to the separation of the flow of the air which enters into the nacelle, so that it leads to a reverse thrust, which leads to bad performance of the engine or the aircraft. So we are need to concentrate more on the diameter of the nacelle as well as the length of the nacelle. Here, just we can find what is we can find what is the critical mass flow rate which is enters into the nacelle structure. Mass flow rate can be calculated using the formula 1 minus 4 into 1 minus DHL, in the sense the highlighted diameter with respect to the maximum diameter, which is represented here, square root of this, with divided by the LF, that is the length of the nacelle with respect to the Dmax, with the whole power 5/2. Whereas the whole process is carried out with respect to the drag of the Mach number. Drag of the Mach number can be calculated with respect to the formula 1 minus 1/8 square root of 1 minus DHL by Dmax the whole square divided by LF divided by Dmax. Here, these procedures are to be carried out in order to find out what is the diameter as well as the highlighted diameter as well as the length of the nacelle, in order to find what is the Mach drag, which helps us in a better flow without any spillage flow. Here, next we are going to discuss about the effect of mass flow ratio, critical mass flow ratio, and the drag Mach number of an axle with respect to the four body design performance. Here, here the graphical representation of the four body diagram with respect to the nacelle has been shown here. Here, with respect to the increase in the mass flow, if the mass flow rate is lesser than the critical mass flow rate, then it helps us in reducing this spillage drag, in the sense when the gases which is extracted by the engine is more, it results in separation of the flow of the gas, which results in reverse thrust, which spoils the efficiency or the performance of the aircraft. So we have to design on the basis which will give a better performance of the engine. With respect to the better performance of the mass flow rate or critical mass flow rate and the drag movement drag of the Mach number, we are just drawn a graphical representation which represents a lower value of the critical mass flow rate and the higher value of the Mach drag leads to a better performance of a free body design drag. Here, if the critical mass flow rate can be calculated with respect to these formulas which we have discussed before itself. Then we have to decide about what is the shape of the inlet lip, in the sense this area is the shape of the inlet lip, where this is the important as well as the major factor which helps us in extracting the air from the atmosphere. So we have to concentrate more on the shape of the inlet lip, in the sense most of the cases it may be a circular path, whereas in major it has to be a elliptical shape. So elliptical shape of the nacelle, that is in the sense the inlet lip is chosen for the process, whereas the inlet lip calculation is carried out with respect to x by a the whole power n plus y by b the whole power n is equal to 1, whereas b is the highlighted diameter with respect to the throat diameter by 2, whereas xl is the length of the nacelle, whereas y is the dmax by minus dhl divided by 2. Here the major whereas A represents the major super elliptical axis, whereas n is the elliptical exponent. Here, with respect to the shape of the nacelle only, we are just deciding about its performance as well as its characteristics. Then we can find out what we need to find out what is the exterior contour as well as the interior contour. Exterior contour and the internal contour, in the sense the surface of the external contour has to be a better surface. It has to be a better surface finish for an external contour, in the sense if it leads to a better drag of the aircraft. So we have to concentrate more on the exterior contour, which results in a better surface finish, whereas the internal contour, here it is the portion which starts from the lip to the throat of the fan, so that internal contour is being calculated with respect to the better surface finish, which will help us in movement of, and that is in the sense drag of the nacelle as well as the aircraft. Then next we are going to deal about the after body design method, in the sense the middle body is only a circular path which we are not going to discuss now. So we are going to discuss about the after body design method. Here the graphic tells the representation of the after body design has been clearly shown here. Here we can calculate what is the length of the aircraft starting from its middle diameter to the exhaust. That is in the sense here the middle part design is carried out at this area before with respect to the front area method. Here LA is calculated. LA is nothing but the after body length, whereas RA in the sense the boat tail radius, whereas D9 in the sense the throat area, which this area is to be connected to the throat of the engine, whereas B here the deflection of this the deviation of this angle, we have to find out what is the angle of this tail angle. This is usually known as the tail angle. It is standardized that it will be not more than 16, in the sense it will be lesser than 16 only. Usually it is known as the final port as well. Then with respect to the after body ratio can be calculated with respect to RA divided by D max is equal to 0.04 divided by 1 minus MDA the whole square. Here with respect to the after body equation, the tan BC is calculated with respect to D max minus D9 whole divided by 2LA. In the sense, D9 is the nozzle exit dia, whereas 2LA is the after body length. Having this data of the forebody design and with the after body design, we are just finding out what is the actual structure of the nacelle. And now next we are going to discuss about the nacelle drag estimation method, which helps us in dragging the nacelle as well as the aircraft with a better performance of the aircraft. Here, the nacelle drag is estimated with respect to the profile drag as well as the wave drag, profile drag as well as the wave drag. If it will be carried out, this nacelle drag will be tested under the conditions of wind tunnel as well as the CFD processes. Here, the air is subjected to directly to the nozzle, so that the analysis part is carried out with respect to the profile drag or the wave drag. If it has been also divided into two parts based on the design condition, in the sense design condition as well as on design condition as well as the off design condition. In the on design condition, if the Mach number is within the limit of critical mass flow ratio and the drag ratio, it leads to a profile drag which helps us in the better performance of the engine. Whereas in off design condition, if the M drag, that in the sense Mach number which is outside the critical mass flow ratio and the drag of the limit leads to a spillage or as the wave drag. Based on the design procedures, the nacelle drag is classified based on the performance with respect to the profile drag or wave drag. Next, we are going to discuss about the forebody drag and the after body drag. Forebody drag in the sense which helps us in finding out what is the drag which helps us in to increase the efficiency, in the sense which helps us in dragging the aircraft in the forward direction. The drag of the forebody drag is calculated with respect to CF is equal to 0.0. Forebody drag is calculated using the formula of density of rho v square A max into C into CD, whereas CD is the coefficient, is the drag coefficient, which will be calculated using the formula CD divided by CF whole power 0.6 is equal to 1 plus 1 by 3 whole divided by 1 minus DHL divided by D max divided by LF divided by D max with respect to into 1 plus 7 by 4 divided of 1 minus MF, that is the mass flow ratio, with divided by the A max divided by AHL minus 1. With respect to the drag coefficient, we are just calculating what is the forebody drag using the formula where the drag, in the sense based on the speed of the engine only, we are calculating what is the area which is required for the nacelle, so that with respect to the velocity of the speed of the engine, we can calculate what is the velocity as well as the density which is flowing mass flow ratio. With respect to the mass flow ratio, we can calculate the body free forebody diagram with respect to the CP, in the sense drag coefficient, whereas drag coefficient is calculated using this formula. Then we are just finding out what is the screen friction coefficient. Here, screen friction coefficient is calculated using CF into S weight divided by A max, whereas S weight is equal to the force body weight area, whereas CF is calculated using 0.455 divided by log RE whole power 2.58. The entire forebody drag as well as the coefficient of discharge is calculated with respect to the Reynolds number. Here, the graphical representation of the diameter of the throat of the nozzle is calculated with respect to the thrust as well as the length of the this diagram represents the length of the engine based on the length of the engine with respect to the engine with respect to the thrust. Here, the first diagram represents the efficiency, in the sense based on the thrust or based on the performance of the thrust only, the diameter of the nacelle is to be carried out with respect to the value y is equal to 1 into 0.0827 into x of 0.432. Whereas this graphical representation shows the relation between the thrust with respect to the engine length. These both are the major values which we are need to consider when designing a nacelle. With respect to the thrust value, the diameter of the nacelle is calculated. With respect to the thrust value only, the diameter and the length of the nacelle is also calculated. Here the graphical representation of the nacelle is shown with respect to the nacelle length is shown with respect to the thrust. This shows a better performance of the engine with respect to y is equal to 2.4077 x of 0.03876. Then we are going to find out what is the critical flow ratio, that is the which we have discussed earlier itself. With respect to the marginal mass flow ratio, if the marginal mass flow ratio increases with respect to the Dmax, in the sense the nacelle drag increases with respect to the mass flow rate, critical mass flow ratio decreases. Usually the critical mass flow ratio will be of a 0.58. The next topic which we are going to discuss about is the GD&T, which is carried out in a nozzle. GD&T is a symbolic, it's a graphical representation of a symbolic representation of a dimension which helps us to communicate from a design engineer to the production engineer, as well as with respect to the process which is carried out to develop a product, so that GD&T plays a wide role in developing a project, in the sense it has to be subjected to certain tolerances in order to satisfy, so that it should not affect the entire volume of the assembly. So that GD&T is the main tool which helps us to translate to the design using some symbols. Here the graphical representation of nozzle has been created, and what are the dimension and the tolerance which can be represented using GD&T. GD&T helps us if we are developing a product, in the sense a part separately, means we can specify what are the dimensions which is applied and what are the tolerances which we can specify over it. Whereas it is a complex assembly or a whole complex assembly, we cannot go for each and we cannot specify the dimensions at each and every part of the assembly, so that we are just communicating to the design with respect to the symbols which is specified over here. With respect to the nozzle dimension, the GD&T tolerance has been represented here. Some of the symbols have been used with respect to the nozzle. Here it is the throat diameter is calculated, is shown with respect to with the symbol, whereas here the fan diameter is represented using the symbol, whereas the radius of this nacelle is represented using RA, whereas these symbols represent the surface roughness of the nacelle, whereas the angle over here is represented using this angle diffraction. Here GD&T consists of 14 symbols through which we can communicate to the design engineer as well as to a manufacturer, so that some of the tolerances should be applied for each and every part, if it should satisfy or if it should be a perfect assembly. With respect to this nozzle, symbolic dimension, symbolic representation of a dimension has been given for a throat value, in the sense here the GD&T is represented, an example of that the diameter is represented using the symbol, whereas this shows the value of the throat diameter, whereas this shows the tolerances value, so that each and every part should be of equal tolerances, or it should be of in the sense variable tolerances is to be maintained, so that it should not affect the entire part of the assembly. Even if small component which affects the tolerances will lead to a major damage in the whole assembly. The next we are going to discuss about the stack-up analysis. What is meant by stack-up analysis? The after process of the GD&T leads to a stack-up analysis. Stack-up analysis, in the sense we are just need to calculate what are the tolerances value which is occurs for the area total assembly. It helps us in finding out the control critical assembly. It helps us in finding out what is the tolerances value for the whole assembly, whereas it also helps us variation of the assembly is also calculated using stack-up analysis, whereas it helps us in finding out what are the rejects which is carried out during the design process, and which leads to a design of prediction changes. Here, the stack-up analysis helps us in finding out the tolerances value of the entire assembly, so that it helps us in reducing the time as well as the stack-up analysis helps us in improvement of a design. Here, the stack-up analysis is calculated using it can be calculated in the 4 type, but now we are going to discuss about one method, in the sense the measuring method, which helps us in calculating using the standard deviation. Whereas stack-up analysis is the of the whole assembly can be calculated using the formula which is represented over here. The square of the standard deviation is equal to the sum of the standard deviation of each part. Here it has been represented. Here the standard deviation of the whole assembly is equal to the square root of the standard deviation of each and every part, which is represented over here. The tolerances value can be calculated with respect to the formula, that in the sense stack-up analysis is calculated with respect to the Six Sigma as well. It has to be, after calculating the stack-up analysis, it has to be subjected through the Six Sigma analysis, where we can find out what is the stack-up analysis which is carried out between the lower limit as well as the upper limit of the area. With respect to the lower limit and upper limit, we can calculate what is the total tolerances which is carried out through to the assembly, and with respect to the assembly of the entire tolerances and the dimensions, we can find out what is the stack-up analysis which has to be carried out in order to find a better performance of engine as well. Then it has to satisfy certain condition, in the sense assembly tolerance should be always lesser than the actual assembly tolerance. Usually, how we are going to calculate the stack-up analysis, in the sense, first find out what is the standard deviation of each and every part of the component, and it has to be summed up and squared up, and it has to be divided with respect to the 6, in the sense it has to be divided with respect to the 6 sigma ratio. After getting the value of the standard deviation, then it has to be multiplied with respect to the value which we have obtained, and it has to be divided with respect to the 2. That leads to a stack up, it leads to a tolerances value. Here, the assembly should be checked before it has to be subjected to the production, so that the assembly tolerance should be always lesser than equal to the 0.6 value, in the sense the 6 value, that is the assembly tolerance should be lesser than or equal to the actual assembly tolerances, which specifies the design is whether reliable or not reliable. If any changes which occurs in the dimension or the tolerances of the each and every part has to be checked over this analysis part, and this has to be carried out process which helps us in finding out what is the design criteria which has to be carried out in the analysis part. After finding out what is the design procedures and the tolerances which is given to a nozzle, then we are going to discuss about what is the design checks which has to be subjected over this area. In the sense, the design check helps us in finding out what are the procedures which we have to carry, starting from its raw material to a finished product. In the sense, it has to be satisfied the inception to the construction value. Inception, in the sense, we may be just start thinking of some of component which we need to install to a assembly, so that starting from a drawing as well as giving its tolerances value, we can find out what is the value, what is the procedure which is carried out from a raw material to a finished product. These design checks helps us in finding out the better performance of the entire part or the assembly, and the results has been subjected to the higher authority of the aircraft agency, so that they will be certifying finally with respect to the perfect standard, with respect to the reliability and the performance of the engine. With this, by this session, we can know or we can be exposure to what is a nacelle structure and what are its type and what is the performance of a nacelle in aircraft. With this, I finish this session. Thank you.